So what we're going to do is we're going to look at what's called an electrolytic cell or electrolysis. The key difference between an electrolytic cell and a galvanic cell, and what we've been looking at so far, is that an electrolytic cell or electrolysis causes a non-spontaneous redox reaction to occur. In a galvanic cell, it's a spontaneous reaction, where my strongest oxidizing agent is a strong enough oxidizing agent to cause my reducing agent to undergo the oxidation reaction. With an electrolytic cell, the combination of oxidizing agent and reducing agents that I have results in a situation where my strongest oxidizing agent is below my strongest reducing agent. And so a non-spontaneous reaction would occur. So if we look at, for example, the combination of two lead electrodes placed into a solution of zinc sulfate, when I look at my entities present, I see that my strongest oxidizing agent is my zinc ion, and my strongest reducing agent is lead solid. My strongest oxidizing agent is below my strongest reducing agent, so I will not get a spontaneous reaction. And I can see this if I put the half reactions together for the two of them. I end up with a overall negative cell potential. Now, since the cell potential is negative and it's not a spontaneous reaction, I have to supply energy. And whereas in a galvanic cell, I looked at having chemical energy spontaneously convert into electrical energy, with an electrolytic cell, I'm doing the opposite. I am using electrical potential energy to force a non-spontaneous chemical reaction. So I'm converting electrical potential into chemical. Okay, and so when I do this, one of the key differences between a galvanic cell and an electrolytic cell is there's only one electrolyte. Now, when we compare the two types of cells, also, we've already talked about how a galvanic cell is spontaneous and an electrolytic cell is non-spontaneous. Galvanic cell has a standard cell potential as positive. Electrolytic cell, it's negative. In both types of cells, my cathode is my site of reduction. The difference is their charge. And their difference in their charge comes from what's going on. In the galvanic cell, I have my oxidizing agent taking electrons from the electrode, and that causes the electrode to have a positive charge. In an electrolytic cell, I'm going to supply the electrons for the non-spontaneous reaction from a power source. In both of the two cells, my anode is my site of oxidation. Again, the difference is their charge. In both cases, the direction of electron flow is the same from anode to cathode, and also the name of the anion comes from what's flowing where. Okay, so let's take a look at a prime example, a potassium iodide electrolytic cell. This is a very common one that we look at. And what we're going to do is we're going to place two carbon electrodes in it so that we don't have to worry about the electrodes interfering with our reaction. When we go about doing these, where we're going to not only sketch it, but also look at the overall reaction and calculate the cell potential required, we will follow the similar steps to what we did with our galvanic cells. Where our first step, we're going to use our cell notation, or we'll make a list of what's present and label our oxidizing agents and reducing agents. Okay, and so in my potassium iodide cell, I have a solution of potassium iodide that I've placed two carbon electrodes in it. So the only things I have present are potassium ions, iodide ions, and water. And I know potassium ions and iodide ions are present because potassium is group 1 and everything with group 1 is soluble. Our second step is, or part of our step is, with our list, we're then going to label our oxidizing agent and reducing agents. Now, in this case, it was relatively easy. We didn't have to use our chart because we know that metal ions from group 1 can only be oxidizing agents. And then non-metal halide ions from group 17 can only be reducing agents because they've already gained an electron. They're not looking at gaining any more. And we know that water can be both. Then what we're going to do is we're going to look at our chart, and we're going to identify where all the things are, and we're going to identify our strongest oxidizing agent and our strongest reducing agent. So my highest on the left, the water, is my strongest oxidizing agent. The lowest on the right, the iodide, is my strongest reducing agent. As we can see, my strongest oxidizing agent is below my strongest reducing agent, so we know this is going to be a non-spontaneous reaction. Okay, but I'll identify my strongest oxidizing agent, strongest reducing agent, and I could even identify the reactions that would occur. Now, the reason that I know that this is my reaction at my cathode is because my strongest oxidizing agent undergoes a reduction reaction, and my reduction reactions occur at my cathode. And I know that this is my reaction at my anode because my strongest reducing agent undergoes oxidation, and my oxidation reaction occurs at my anode. So now I know my two half reactions, and I know what my things are. Okay? We're going to write down our reactions. Okay? We're going to balance, and when we balance, we know that we have to make sure that my electrons gained are equal to my electrons lost. So in this case, it's the same. So all I have to do is add my two half reactions. And I can also determine my cell potential where I add the cell potential from my reduction reaction to my oxidation reaction. And again, I can see it's a negative value, so therefore I know it's a non-spontaneous reaction. Okay, and we're just going to look at our chart again, make sure things line up. Non-spontaneous, negative value, our sites. Now, when I go to label my diagram, I said that I place 2 carbon electrodes into a solution of potassium iodide. So I have my potassium ions, my iodide ions, my water. I have my power source, and I have my 2 carbon electrons. Now, if we remember from electricity way back in grade 9, we know that this is the negative terminal of the battery. This is the positive terminal. So the negative terminal of my power source of my battery is going to have a buildup of electrons. Those electrons are going to be repelled and travel down the wire into this electrode, and as a result, it will have a negative charge. At the same time, this is my positive end of my power source of my battery. They're going to attract the electrons out of this electrode, and so this electrode is going to have a positive charge. Now we know from above that my negatively charged electrode is called my cathode. Okay? And my positively charged electrode is called my anode. We also know at my cathode it's the site of my reduction reaction. And so we can show our water going across and undergoing its reduction reaction to produce our hydrogen gas and our hydroxide ion. Okay? As we said before, my positively charged positively charged electrode is my site of my oxidation reaction. So I know this is my oxidation reaction. So we can have our ions travel across and undergo their reaction. Okay. One of the things that we have to watch out for with our electrolytic cells is water. If I have a electrolytic cell and I want to produce or force the non-spontaneous reactions where I have the reduction of any of the metals in my chart that exist below water, I can't do it if water is present because water would be my strongest oxidizing agent and it would be in the way of the reaction. So let's say I wanted to force a reaction where I caused my calcium ions to undergo a reduction reaction. They could not be aqueous. I'd have to take a salt, for example, calcium chloride, because I can also see chlorine is above water on my reducing agent, so water would get in the way if it was aqueous. But if I took calcium chloride and I melted it, and I made molten calcium chloride, then I'd only have calcium ions present, and I have chloride ions present. Water would not be there to get in the way, and I could then force the reduction of calcium ion and the oxidation of chloride ion. Okay, so anything above water, any reducing agent above water, or any oxidizing agent below water cannot be produced through a electrolytic cell if it's through an aqueous solution. It has to be done through a molten salt, where I take an ionic compound and I melt it. So let's take a look at one more example quickly so that we can just confirm our understandings. So this is similar to our standard notation that we had before with our galvanic cell, where I have my anode, I have my cathode, and then I have my electrolyte. Because there's only one electrolyte, I don't have a salt bridge, and I don't list the other electrolytes. However, okay, so I have my anode, my cathode, my electrolyte. So I know that this is going to be my site of my oxidation, this electrode. This electrode will be my site of reduction. Because they're both platinum, I know that the platinum is not present in either my oxidation reaction or reduction reaction. So therefore, I have to look at my electrolyte and the ions present as well as the water, because it's aqueous, to therefore determine what my reduction reaction and oxidation reaction is. So first I list what I have. I label it as an oxidizing agent or reducing agent. Okay, I can look at my chart, but I can also know group 1 metal ion can only be an oxidizing agent. Water is both, so I only had one thing to look up. And then I'm going to look on a chart and identify my strongest oxidizing agent, my strongest reducing agent, and I'm going to write out their half reactions as well as their cell potentials, since I know that I'll need them. Okay. Now that I know my oxidation half reaction and my reduction half reaction, what I can do is I can first get my overall reaction and my cell potential, since I need that, and then I'll go on to label the diagram. Now, I have to make sure that my electrons lost equal my electrons gained, so that I'll multiply my first equation by 1, my second equation by 2, combine them, and then I have water and hydroxide on both sides, so I'll reduce, and I get this overall reaction. And then I can also determine my cell potential. So I would have to add 1.23 volts minimum to force the hydrolysis of water, and to have water break down into oxygen and hydrogen gas. Okay, so now we can label our diagram. Okay, so I have my sodium ion, I have my hydroxide, I have my water, I have my 2 platinums, I have my power source. Okay, again, this is my negative terminal, so it's going to push electrons into this electrode. This is my positive terminal, so it's going to pull electrons out of that electrode. So therefore, this electrode will have a negative charge. This one will have a positive charge. Okay, because this is my negatively charged electrode, I know that this will be my cathode. Since this is my positively charged electrode, it's my anode. I know that my cathode is the site of my reduction, so I can show my reduction reaction. I'll show the movement of the ions or the water across for the formation of the products. I know that my anode is the site of my oxidation, so I can show my ion move across and undergo oxidation for its product. Okay, I can write my overall reaction underneath, and near the power source, I can also write the cell potential required.